Imagine you have a law of physics that has held perfectly true for, well, for over a century.
Right, the kind of absolute bedrock rule you build your entire understanding of the physical world on.
Exactly. Every textbook treats it as total gospel. And then, you look at a tiny speck of perfectly clean graphene in a lab, and this century-old law doesn't just bend
No, it doesn't just have a slight margin of error, it completely shatters.
by a massive factor, like over 200 times what it should be.
Yeah, it is basically the equivalent of dropping an apple and watching it shoot upward into the atmosphere at 100 miles an hour.
But it's wild.
When a fundamental physical law breaks by a factor of 200, it forces us to reconsider the actual bedrock of reality.
And that is exactly what we are exploring for you today on this deep dive. We are synthesizing a really fascinating stack of fresh white papers and preprints.
They're all analyzing this phenomenon called quantum critical transport in graphene.
Right. But we aren't just here to talk about a quirky piece of material acting up in a laboratory. Our mission today is to unpack how this specific anomaly might actually be, well, like a rendered laboratory.
A smoking gun proof, really.
Exactly. Proof that our universe doesn't operate as a smooth, continuous vacuum, but rather on a framework of discrete, token-based physics.
Specifically, something called the tetrasphere interpretation and the twist model.
So to understand why scientists were so completely caught off guard by this, we have to establish the baseline of what was actually supposed to happen, right?
Yeah, the shattered rule in question is the Wiedemann-Franz law.
Classic textbook physics.
Right. For over 100 years, this law has dictated that in ordinary metals, electrical conductivity and electronic thermal conductivity are inextricably linked.
So if it conducts electricity well, it conducts heat well.
Exactly. If a piece of metal is a good conductor of electricity, it is inherently a good conductor of heat.
Because they are relying on the exact same mechanism. Let's use an analogy here so you can really picture this. Think of a standard metal like a busy highway.
Okay, I like this.
And the electrons are a fleet of delivery trucks. Now, these trucks are tasked with carrying two different types of cargo simultaneously. They carry letters, which represent the electrical charge,
Right.
and they carry heavy boxes, which represent thermal energy, the heat. If that highway gets bumpy.
Like if the material introduces resistance.
Exactly. Both deliveries are going to slow down proportionally. The letters and the boxes share the exact same fate because, well, they are riding in the exact same trucks.
That is the Wiedemann-Franz law in a nutshell.
Right.
And it is a solid assumption for continuum physics. But then researchers looked at ultra-clean graphene near a very specific state called the Dirac point.
Let's define the Dirac point really quickly for anyone who might not be familiar. We are talking about a state of perfect charge neutrality. The temperature is extremely low, and the system is perfectly balanced on a tightrope between negatively charged electrons and positively charged holes.
And in that perfectly balanced, ultra-clean environment, the researchers measured what is called the Lorentz ratio.
Which is just the math comparing the heat and charge transport, right?
Exactly. It's simply the mathematical relationship between the two. Now, if the Wiedemann-Franz law holds, this ratio should hit a standard, predictable, semi-classical value.
But it didn't.
Not even close. The ratio exploded. It exceeded the normal value by more than 200 times.
100 times.
The researchers observed heat flowing incredibly easily through the graphene, while the electrical charge was severely, severely bogged down.
So going back to our highway analogy, it's as if those delivery trucks are somehow managing to deliver all the heavy boxes of heat at lightning speed. But the letters representing electrical charge are just stuck in a massive traffic jam.
Yeah.
How is that physically possible if they're supposed to be the exact same trucks?
Standard physics struggles deeply with this. I mean, the mainstream consensus labels this a strongly interacting Dirac fluid regime.
Strongly interacting Dirac fluid regime.
Right, basically suggesting that the charge and heat currents have somehow decoupled.
But I have to say, that sounds like a label, not an actual explanation.
Oh, it absolutely is just a label.
Yeah, calling it a strongly interacting Dirac fluid regime is just giving the mystery a fancy name. It doesn't actually explain the underlying mechanics of why the heat is moving and the charge is stalling.
It doesn't. And to find the actual mechanics, we have to abandon the idea of continuous space entirely.
Okay, here we go.
This is where we bring in the Gibsonian, or tetrahedral, token framework. We literally have to change our entire ontology of reality.
Which is a big ask.
It is. But in this model, space itself is not a smooth, empty vacuum where particles just float around. Space has a chunky, discrete structure.
Chunky space.
Right. It is built from microscopic S units arranged in what's called tetrahedral adjacency.
Okay, so I am looking at the papers here, and they are throwing around terms like tetrahedral tokens and modulo 4 cycles. I want to push back on this a little because physicists invent crazy, complex math all the time just to fit weird experimental data.
That's a fair point.
Why should you or I believe that space is actually a chunky grid of microscopic pyramids just because of one graphene anomaly? Are we really arguing that reality operates like a cosmic video game engine?
The video game engine analogy is actually incredibly apt.
Really?
Yeah, and here's why we should take it seriously. Continuum physics, the idea that space is endlessly smooth, fails to predict the numbers we see in graphene without inventing increasingly complex patch fixes.
Right, they just keep adding math.
Exactly. But the discrete model doesn't invent new forces. It actually redefines motion as a strict accounting process.
An accounting process.
Yes. In this framework, what we observe macroscopically as a moving electron is just rendered space.
Like pixels on a screen.
Precisely. But underneath, in configuration space, a local site in this tetrahedral grid only advances when it receives a specific set of token inputs.
Okay, let's explain this like I'm 5 for the listener. If I zoom all the way down into this microscopic grid of pyramids, what does a token input actually look like?
So the process is governed by the wedge cycle protocol.
Wedge cycle. Okay.
Think of a single tetrahedral site in the grid, like a microscopic toll booth. A fill is a unit of incoming data or energy.
Got it.
The wedge is the actual mechanical processing of that data by the site. So for the toll booth to let a particle pass through to the next site, it requires exactly 4 fills and 1 wedge operation.
Wait, 4 fills and 1 wedge?
Yes, that nets a +3 scalar gain, which basically updates the state of its geometric faces on a modulo 4 cycle.
Let me stop you there. Modulo 4 cycle. That just means a 4-step loop that resets, right? Like counting 1, 2, 3, 4, and then back to 1.
Exactly. It's a strictly defined accounting loop. The ledger must balance before motion can even occur. And this completely redefines what a straight line is in physics.
How so?
Well, in a smooth, continuous universe, an object moves in a straight line. A geodesic, because it is the shortest distance between 2 points in an empty vacuum.
Sure.
But if space is an endless grid of toll booths running modulo 4 accounting cycles, nothing is truly empty.
So motion isn't just floating through a void. Motion requires constant active processing by the space you are moving through.
Yes. A geodesic in this model is simply the path of least resistance. It is the path that minimizes what the model calls inversion stall burden.
Inversion stall burden. Okay, mechanically, what is that?
It is the computational cost of keeping the tokens moving.
Ah, the toll booth fee.
Right. Every time an excitation, like an electron, tries to move, the underlying grid has to update its faces and process the tokens. If the instructions moving through the grid are simple and unified, the toll booths process them quickly.
And if they aren't?
If a path requires complex, contradictory reconciliation, the accounting process stalls out. It incurs a massive inversion stall burden. So objects naturally follow the paths that are cheapest to process in the ledger.
So the universe is basically incredibly lazy, seeking out the absolute cheapest accounting path to render motion. I can wrap my head around that. But here is the critical test for any theory.
How does it explain the graphene?
Exactly. How does this token ledger perfectly predict why the graphene highway jammed up for electricity but not for heat?
It all comes down to the specific instructions, or currency, trying to move through the grid. Let's look at the electrical charge channel first.
Okay.
The token model defines an electrical current as a signed rapallonomy current.
That is a dense phrase. Signed rapallonomy. Break that down.
Signed is the key word there. It means this type of current cares deeply about positive and negative signs.
Okay.
Now remember this specific state of our graphene near the Dirac point. It is parity-balanced. It have an equal, highly active population of negatively charged electrons and positively charged holes.
Right. It's a perfectly symmetrical environment.
Exactly. When you apply an electric field to this graphene, that field gives contradictory instructions. It tells the negative electrons to move in one direction, and it tells the positive holes to move in the exact opposite direction.
Because opposites attract and likes repel in standard electromagnetism.
Correct. But because the medium is so perfectly balanced and incredibly active, the underlying token ledger is constantly receiving contradictory commands.
Oh, I see where this is going.
The toll booths are trying to process positive tokens moving left and negative tokens moving right at the exact same time in the exact same space.
They're jamming the toll booth.
Exactly. The model calls this being parity frustrated.
So the accounting system just crashes.
It faces a massive inversion cost, quantified mathematically as gamma q. The tokens cannot reconcile the contradictory commands efficiently at all.
So the processing burden is astronomically high.
Right, so the local sites stall out, the rendering of motion slows to a crawl, and electrical conductivity plummets.
Okay, that makes perfect mechanical sense. The grid is overwhelmed by trying to tear these perfectly balanced opposite charges apart. But what about the heat? Why does heat flow through this exact same parity-frustrated grid without any issue?
Because heat transport provides a completely different instruction set to the ledger. Heat transport is defined as an unsigned full complement redistribution current.
Unsigned, meaning it completely ignores whether a particle is an electron or a hole.
Exactly. A temperature gradient does not ask the system to separate positive and negative charges. It simply asks the system to move entropy and enthalpy.
It just wants to move vibrational energy.
Right. In this scenario, the negatively charged electrons and the positively charged holes can flow in the same gross spatial direction to transfer that heat. They aren't fighting each other's directional commands.
Oh, I see. Let me try to synthesize this for you listening, because this is genuinely the absolute aha moment of the entire deep dive.
Go for it.
Imagine a giant, crowded dance floor packed with couples. If you get on the microphone and tell all the partners to separate, say, all the leads have to run to the left wall and all the follows have to run to the right wall, it is going to be chaos.
Total gridlock.
Right. People are going to collide endlessly trying to cross the room. There is going to be massive friction, high frustration, and a huge stall cost as they try to navigate through each other. That is our electrical charge trying to move through the parity-balanced graphene.
And the heat.
The heat is just the energy of the music. If you want the energy of a beat to wash across that same crowded room like doing the wave in a stadium, you don't ask anyone to separate.
They just stay where they are and move together.
Exactly. The couples just pass the rhythm along in the same direction. The positive leads and the negative follows move cooperatively. The energy flows flawlessly from one side of the room to the other with almost zero friction.
That analogy maps perfectly to the token mechanics. Because the electrons and holes are moving cooperatively to transfer heat, the current is protected by what the model calls complement throughput.
Complement throughput.
Yeah. The toll booths are processing unified parallel commands. Therefore, the inversion burden gamma H is incredibly low. Heat flows freely.
And this circles us all the way back to why the Wiedemann-Franz law shattered. The century-old law assumed that charge and heat were physically locked together as the same fundamental property of a moving electron.
It assumed they use the exact same accounting ledger.
Right.
But ordinary metals create an illusion. They have a massive excess of one type of carrier, usually electrons.
So it's mostly just leads on the dance floor.
Exactly. Because the environment is so heavily skewed, you don't notice the friction of separation. The different token channels are blurred together by brute force. Graphene, by being perfectly parity balanced, strips away that macroscopic blur. It proves that charge and heat are distinct channels that completely split under the right conditions. You have a high-cost, sign-dependent channel and a low-cost, unsigned channel.
Predicting a qualitative split is a massive victory for the discrete token theory. It gives us the mechanical why, but we haven't talked about the most compelling part of this research yet.
The numbers.
Right. If this discrete space theory is real and the universe is running a literal accounting ledger, then there should be a bottom line numerical budget. And that is where the Quist model comes in to actually spike the football on this whole debate.
The quantitative data is really what elevates this from a neat hypothesis to a true smoking gun.
Yeah.
In the experiment, the researchers found a second major anomaly. They measured the quantum-critical conductivity of the graphene in this state, and it converged to a very specific universal value across multiple, completely different devices.
And what was the value?
It converged to roughly 4 times the elementary charge squared, divided by Planck's constant, 4e squared over h.
Now wait. Standard physics tells us that electrical conductivity depends heavily on the specific sample of material you are testing, right?
Oh, absolutely.
If a piece of metal has more microscopic dirt or structural defects or scratches, it conducts differently. Why would multiple physically distinct graphene devices spit out the exact same universal number?
In continuum physics, explaining that convergence is an absolute nightmare. But in the twist formulation, which models these underlying discrete dynamics, this convergence is exactly what's expected.
Why?
Because the graphene is ultra-clean and perfectly balanced. The flow of energy stops being defect-dominated. Microscopic junk in the material is no longer the limiting factor. The flow becomes closure-dominated.
Let's break down closure-dominated. What is a closure loop in the twist model?
So in a discrete grid, a particle or a current isn't a solid object. It is a path of tokens that must perfectly self-reconcile to maintain stability.
Reconcile, like balancing the books.
Exactly. Think of it like a ledger balancing out to exactly zero at the end of the day. A closure loop is the mathematical necessity of the token path closing perfectly back on itself in configuration space.
So if the material is incredibly clean, the tokens aren't fighting the material anymore. They're just fighting the fundamental rules of the grid itself.
Exactly. The 4e squared over h value isn't a measurement of the graphene's impurities at all. It is literally the fundamental conductance budget of the underlying rendered lattice.
That is genuinely wild.
The geometry of the universe's token grid is mathematically exposing its own baseline limits to us. We are looking directly at the maximum processing speed of the toll booths.
The grid is just showing its math.
It really is.
Yeah.
And there's a final piece of evidence that locks all of this together mechanically.
What's that?
The researchers also measure the fluid's viscosity to entropy density ratio. This is often written as eta over S. Viscosity is how thick or resistive a flow is, and entropy density is the amount of thermal disorder.
Right.
They found that this ratio approached a known minimal dissipation scale, which physicists call the holographic benchmark.
Basically, continuum physicists look at that benchmark and say, wow, that is a nearly perfect fluid, but they don't really know why it's perfect, do they?
No. But the twist model knows exactly why. If a flow hits the holographic benchmark, it means the collective energy has found a highly stall-efficient geodesic.
The path of least resistance.
Yes. It is successfully moving momentum with the absolute minimal, irreversible degradation of tokens. It has found the mathematically cheapest possible path through the discrete ledger.
Let me pull this all together for you listening, because the picture forming here completely changes how we should view physical laws. The twist model dictates that high closure complexity requires a high token budget, which causes resistance and stalling.
Yes, the ledger gets overwhelmed.
And this graphene experiment physically manifests that rule in the real world. The electrical charge transport requires tearing apart perfectly balanced positive and negative signs. That is a high-twist, highly complex accounting operation, so it crashes.
Exactly.
But the heat transport just requires moving complementary energy in unison. That is a low-twist, low-complexity operation, so it thrives and hits near-perfect fluidity.
Nail it.
And every behavior we've discussed is governed by the universal invariance of discrete, chunky lattice, right down to the specific universal limit of 4e squared over h.
The math and the physical reality align perfectly. Graphene, in the Dirac fluid state, is not an exception to a rule. It is a lens that strips away the messy, macroscopic blur of ordinary matter and shows us the actual gears of reality turning underneath.
So if you're listening to this, why does this deep dive matter to you? The big takeaway is that this single shattered law acts as a bright lantern held up to a discrete universe. It proves that foundational absolute continuum transport laws, things like the Wiedemann-Franz law that we have trusted for a century, are actually just emergent approximations.
They are macroscopic illusions.
Wow.
They only look like unbreakable laws because ordinary environments are messy enough to blur the different token channels together. When you have a massive excess of one type of carrier, the sign-dependent electrical channel and the unsigned heat channel are locked together by brute force. But the moment you create a perfectly balanced environment, that illusion shatters. The true discrete token economy reveals itself.
Which leaves us with a truly profound question. If one of our most trusted laws of physics turned out to be nothing more than an emergent illusion, just two independent token channels that we mistakenly thought were one, what does that mean for the rest of reality?
It suggests that many of our fundamental forces might just be macroscopic accounting errors.
Think about the absolute forces you experience every day. Think about gravity pulling you down. Think about the arrow of time constantly moving forward.
We experience them as continuous fundamental forces of a smooth universe.
But if space is just a ledger of tetrahedral tokens running modulo 4 accounting cycles, are gravity and time truly fundamental? Or are they too just temporary macroscopic illusions of token flows?
Are they just waiting for us to find the right extreme environment, the right experimental lantern, to watch them split apart and reveal the discrete, ticking clockwork underneath.
Imagine building an experiment under the exact right conditions and finding out that time or gravity is just a happy accident of a complex ledger, something for you to ponder long after this deep dive ends.